Good morning and good evening to all. Thank you very much for joining us today. This is our 24th talk in the joint webinar series between Binghamton University and VIT. Dean Vasudevan and I are delighted to welcome you to today's webinar. Today we are glad that we have a speaker from VIT, Dr. Fathima Patham, who is an associate professor in the Department of Design and Automation in the School of Mechanical Engineering at VIT. She has joined VIT since 2018 as an associate professor. She received her Ph.D. and Master of Engineering from the National University of Singapore in the field of nano-conventional machining. Her postdoc was in the field of optical fabrication and testing in Germany. The main objective of her postdoc was to build machines with artificial intelligence. During that time, she was employed as a research scientist in Zico in the UK for building Zico robot polisher with AI. Her main research interests are robotics, AI, and additive manufacturing. She's currently working on designing lightweight structures for aircrafts and space robots using topology optimization and fabrication of structures using additive manufacturing. So without further ado, please join me in welcoming Dr. Fathima to our joint webinar series.
So good afternoon and good morning, everyone. My topic is topology optimization for lightweight structures. So what I'm going to do here is I'm not going to show you like with a lot of results, because you know that we all have a difficulty due to pandemic, going to the lab, printing, testing, so many things. But my main interest is always AI, and I'm going to show you what I am doing currently in this. Okay? So my introduction starts from direct digital manufacturing. You all know that what is direct digital manufacturing. That means it is a major part of Industry 4.0. Industry 4.0, what we get is, that is, the main objective is reducing human interactions or giving artificial intelligence to machines. So the machine can decide on their own design or help the designers and help the manufacturers and producing products with less defects and high efficiency. That is the main objective. So here, direct digital manufacturing, it is a DDM, short form of this. First of all, we need to design what we need right now, what we want really. Machine doesn't know, or artificial intelligence doesn't know what we want. We need to teach the system what we really want. So today's technology, this slide explains today's technology. For example, you can see here, just you have to make the design what you want right now. Then there are softwares available for form optimization. Maybe you can take one example. There are many kinds of optimization like form, shape, and structures. I'm not going very deep into that. So for example, you can take form optimization for this component. Then we can go for like 3D design. Then we can optimize the design. Then we can go for like detailed drawing or whatever slicing it's called. Then you need to create toolpath. That means before the toolpath, you can also, suppose if you want to use additive manufacturing, we can go for like slicing. Then you can make a toolpath. Then that's all. Once it is done, then quality control, then technical document, marketing and shipping, etc. So here you can see that you can clearly have two lines. One is above. See, just follow my cursor, above and below. So above is my interest and below is not my interest. Okay, because I am not very skilled in this quality control marketing. But I am very much interested in design, and I wanted to explore the possibility of the design right now, and what you have to do, and where there is a gap between this. We cannot just go and apply artificial intelligence and just say how much you can rely on the designs, how much we can rely on the software currently, or how much we can rely on these softwares. Directly you can just going to print, but is it okay? Is it the final thing? So that is about my talk and my research. Okay, I don't want to go about what is additive manufacturing. We know, every one of us, we know we just put material, and this is subtractive. Just we put material and we eliminate whatever the part of the solid block we do not want, then we can get a 3D object. So we claim that there are a number of total wastes or more, and it is not good for environment or whatever you can call it like this. Instead, the process B is just you have materials, that means in the powder form, then we can go for additive manufacturing, and we can get the object and we can get the less waste. But it is not only the objective, but it is the to understand what is the difference between subtractive and additive manufacturing. So now, what is additive manufacturing? Additive manufacturing is the term we know before, since 10 years we are using the term. But before that, what we are using is, most of us are very, very familiar about rapid prototyping. When I was a PhD student, we have our new machine that's for people who are working day and night for just creating the cell phone covers and designs and everything in rapid prototyping. I have only that memory of rapid prototyping, but you know that rapid prototyping is a very, very good tool to start your product. Okay, just we don't have to go to any product. Maybe you can use it for subtractive manufacturing also, but if you want to visualize this, your product, the very good way and the excellent way is the rapid prototyping. So this is the object. First of all, you need to design the object and print it. That may be like sintering. Mostly they are using sintering. Before that, now we are using 3D printing with fibers, right? Before that we use sintering. Then mostly we use plastics, and we can visualize the product. But the product is only prototyping. You may not use that one. Then we have to add the tooling and manufacturing aids. Then finally you will get the product. So what is the difficulty of this? Really, there is a difference between rapid prototyping and additive manufacturing. Yeah, yes or no. We can say we cannot differentiate both of them. So here you can see that what is the big advantage of using additive manufacturing? Additive manufacturing increases the design freedom. Okay, whatever you want to design, which shape you want, you can just manufacture, or you can get a prototype out of additive manufacturing. You can use any technique, 3D printing or additive. You can use it powder or a fiber, whatever it is, you can use it. Okay, that is the difference, but it is not a very big difference. So I just wanted to introduce our part. My interest is only the design. So currently what we are doing, there are two possibilities to modify the design. For example, you see this part here. It's just look like, for me, like a connecting, just a lever like that. So here, before that, what we are going here is we design this, then we can go for forming, then we can go to foundry and just we use the pattern, then we can get this. So this is the product so far what we are having. Then after that, once we find additive manufacturing, there are possibilities to remove the excess of material, excess of weight, and save the material by just modifying the design. Okay, so for this we call it as like topology optimization. So far I know. So what it does, we need designers because we need this design and we need software. So for example, like FEM, ANSYS, so we can just use that one. So the designer should work on this and the software to get the final part like this. So this is all about design. Then topology optimization, what we need is designers, first of all, design the initial thing. Then they can use the topology optimization software. Then they get the unwanted portion removed. Then they have to redesign. So this process is completely known as redesign. So the first part, this and this, you can achieve by topology optimization. Then you can print it. That means you can fabricate using additive manufacturing, and still you can use even foundry, old method, forming, everything you can use it for this. Even machining is possible, I guess. Okay, the second kind of design is called generative design. Okay, what is generative design? As we discussed, direct digital manufacturing, in here, we are using only complete AI assisted. Okay, so here is just an example for this. So you can see here, this is the original component. It is just like a clamp, just like a clamp. And then what you have to give here, it is an intelligent system. See, you have to give the forces and the boundary conditions. That's all you need to give. You don't have to describe anything like that. Like you don't have to give a design like that. So just you have to give what you really want, where the forces are applied, and what are the boundary conditions, and what are the limitations for this. So what you will get is, see here, you can get lots and lots of design suggestions. You can pick either 1 or 4 or 8, whatever you want, you can pick it up. Hundreds of designs you will get by using artificial intelligence. So now you are really confused. For example, here, at least 50% of the work is done by you, and you are confident enough that it is not very much different from this. At least it looks like that. But here, suppose, for example, in generative design, the chair, what we are sitting, chair, may be different, very, very different. Maybe it has no legs, or 1 leg, or 2 legs, or even, I don't know, it just like looks. Then how we can find it out? And how competent we are using generative design? It is a big question mark still now. To me, at least to me, I am not saying everyone is having this. So these two methods, we can get designs for additive manufacturing. So what is the big deal? Now you can ask me, what is the big deal? Okay, we can do either, we can select like manual method, 50% manual method with assisted software, or we can go for like generative design. We can do this with that. So what is the difficulty and where is the difficulty? Okay, now let us see what we are doing. Maybe I am doing here. Okay. So the main objective, what I see it is in a very different view. The main objectives in our design and Department of Design and Automation at Vellore. First of all, we want to know the limitation of D is missing. So limitation of digital design. What is digital design? We are using AutoCAD or so many softwares since like 23 decades, right? We are using. Now, what is the difficulty? I'm not talking about just drawing softwares. I am talking about this. Design for additive manufacturing. And how to validate or evaluate the design. For example, if I get this, okay, I'm happy because it looks like me. For example, the design is excellent. Okay, I got something. I can print it out. Or I can use this one, the software. I pick design 1, I don't like design 4, I pick 100. I can choose anything, but how can I evaluate this? Okay, that is one of another question I got. Then the next thing is comparison between available design softwares. Okay, you have this, you have that. I don't want to name it, but you have this, you have that, and which one is good? Really, which one solves my problem? Okay, so we try this one also to find out, okay, how much we can rely on the softwares. The next thing is there a possibility to evaluate the life cycle of the components designed using design for additive manufacturing methodology? See, for example, I manufacture this. I know what is the life cycle of this one because since 100 years I'm using this. But I spend a lot of money, okay, for my vehicle, for my application. I get this fancy design, but I do not know anything about the life cycle of this component because one part of this may cost a lot. What I can do, I have two choices. Either I have to just believe this system, I mean the design, then I have to go ahead and find out on my own. Okay, and for here, I do not know anything about which design is good, which design is suitable, but I have hundreds. And my job is getting really very, very difficult when I am going to evaluate all these designs. Okay, so the life cycle, as we all know, life cycle is a very, very important criteria in design. These 4 points I am concentrating, and I think that these whatever I have written here are very, very important when you want to really go for whatever you call additive manufacturing to get a high efficiency. Without design, you can't do anything. Your job is a failure. Without you can't produce life cycle, the process will be a big failure. Okay, so how we are doing, how we are trying to work in this is my research here. Okay, just what I am having a team of people here. I just wanted to introduce. I think they are sitting here and listening the lecture, I guess so. So I am working with Nizar Alam Khan. He's a MTech student, Shashwat Verma, MTech student, and Surab, BTech. Harsh is BTech, and Naman Sharma also BTech. So every one of us are talking, and really they are doing really wonderful work, and I really appreciate their work here. I wanted to say thank you for their hard work. So first of all, what we are main objective here is design for additive manufacturing. Just we want to experiment. See, the first one is what we are using is topology optimization, current methodologies, and software. First of all, we need to know what are the things available in our system, and is that enough, and am I satisfied? It is giving me confidence to go for additive manufacturing products, for lightweight product. If I have a spacecraft, can I just an order from this? For example, ISRO, I can get an order and I can manufacture and I can do it or not. I have to produce my own software. How much I have to put my engineers, how many people I have to employ. So many things a company must think of when they want to go for additive manufacturing, complete additive manufacturing I'm talking about. Then customizing the topology. What is customizing the topology? What we really wanted to do. See, another thing is going on, lattice structures. People want to introduce, just please excuse me, I want to go back here. See, this is just like grids supporting structures like that. But you already know that if you fill this empty spaces with lattice structures, just imagine here like a honeycomb. Just I am putting the honeycomb in between all the gaps. It will give definitely a strength, and that one is possible. Yeah, that is really possible because many research show that it is really a perfect design. Okay. So what we are going to do here is see. We want to optimize the lattice structures based on material. For example, if you use aluminum, if you have like only one lattice structure and if you want to use it something, and here also you get confused. There are many lattice structures available. You can choose it, but we have to experiment our own things. For example, if you take aluminum, this one is like the lattice structure is perfect. For this material, this is better, something like that. Okay. So what we are trying here is customizing means we just want to create a library for materials and the perfect lattice structure for that material. So that's what we are also concentrating on. The third thing is introducing. For example, I already showed that example, and here what is missing? The missing points are there is no, okay, once again, please excuse me. I'll go here. You can see that just if you just give this as input and this is as output, and even you modify, remove something here. For example, this is removed and it is connected like that, also possible. See why we need like this. You can also connect from this to this one line. You can connect. But here what is missing is how we can use the tools. There is no information. See, for additive manufacturing, there are a lot of limitations. You know that if it is inclined 45 degree and more than 45 degree, less than 30 degree, what we need is supporting structures we all know need or not. And if it is a oval shape, circular, in what way you need to print. So many things are there. As well as, suppose if you want to produce this component using CNC, or you can use even foundry, for example, for this part. So there is no information about how to manufacture this. It's just giving this. Okay, manufacturing and cost-effective concept. We want to introduce some manufacturing concepts. What we are going to do is we are going to modify the topology optimized structure, and we are going to just insert this concept and we are going to test it. So for that we are using the language TCL, and we can see it later on. Okay, so we are concentrating three things here. One is current methodology and comparison of software, material-based lattice optimization, and another one is introducing manufacturing cost-effective concepts. Okay, first of all, we can see this topology optimization using current methodologies and software. So here there are two components. This is static, this is upright, and this is a wheel hub, I guess. And just what we are using is we used topology optimization software to remove excessive, I think the less stress area here, and we optimized the structure. We got this one like this. Then we can redesign, and this is the final part. We can get that. We just eliminate the sharp edges and this. So this is the project work of my final year project students. So they got this one. Okay, perfect. Now they reduced a lot of weight and everyone is happy. And here this is a dynamic component and wheel hub, and here what they are using here is like that. They got the final product like this. So are we happy with this and this? What about the life cycle of this? What about the tool constraints. What about the manufacturing constraints in this? How we can find out this? Okay, so next thing is they even used, see mesh, I will zoom it so you can see. See, they are using lattice structures and also find interesting results. Everything is on the computer. Everything is on the computer. It gives some values, so you can see here. See, this can be manufactured by additive manufacturing. I'm very, very sure. I'm not denying anything, but what about? Okay, so just this is the comparison of software. So whatever you want to use, but you cannot get anything about the efficiency of this component and the life cycle of this component and what are the manufacturing constraints used for this component. It's a very good example. So here you can see that the points may be like here and this and that. See, look at this. These are all weak points. Every designer knows this one is a weak point. So what is the life cycle? How we can know that? Is it okay? We have no idea about this. So this is the first part. With this question, I complete the first part. And the second part is, can we solve it? So the second part of this is customizing topology optimization. So what we are using is here is material-based lattice optimization. I just wanted to, this is not completely done. We are doing it. I just want to know this. Okay, what we are using is here, there are like two stages. First of all, it is the conventional way. And first of all, we use modeling, meshing, pre-processing, applying boundary conditions, solving, then topology optimization, then we can printing, post-processing. This is the very, very conventional way. That means without any lattice structures or meshes. But our aim is to mix this unit cells inside this one, like lattice structures. So we are trying to create a library, and we are going to test with the library. I mean the unit cell library. See, this is the structure, lattice structure, and for the material, which one is better. So we are currently doing this. We are not at all completed. I just want to show you some results, interesting results we got. That's all. So then we can introduce this one. Then we can generate mesh. Then the process is going like same, introducing lattice structures, and we analyze using FEA. Then we repeat until we get the final optimized shape. So this is our focus here. Okay. So for example, this is one of our results. We are using a titanium, I guess, and the dimension is 25 mm cube, and the initial mass is like 69.21 grams. And after applying our lattice structure and all, I think the weight is reduced to 12.352 grams. Then after that, you can apply all the FEM, your boundary conditions, everything, and you can apply it on your real object. So this is what we are currently doing, but it is still not over. It is under processing. Okay. So our aim is like, first of all, like material, whatever the material, like especially we are focusing on aerospace, then we can use artificial intelligence to match the lattice structure as well as the material. It will give some suggestions like the generative design. Okay, this lattice structure, you can use it for the material, or this is better, something like that. Then we will get optimized lattice structures library. That's our aim. Okay, by this, I close this second part of our research. Okay, so these are some outcomes. and comparison for the part like this one. So here we got some interesting results. Some results, okay, interesting. I don't say interesting, but we got some result to analyze. Cost reduction, tool manufacturing, something like this is what we got right now. And the third part is introducing manufacturing and cost-effective basic concept. So we are introducing TCL, we are using TCL to get the concept. So here, the third part, we are interested in using topology optimization with multi-joints and multi-material constraints. Okay, so the topology optimization fails to consider the manufacturability and manufacturing cost. We already discussed about all these things. Topology optimization does some only one objective weight reduction. Okay, but it doesn't care about you can manufacture the product or not, and what is the manufacturing cost is going to be. It doesn't care about this. But as a manufacturer, you need to know everything before you want to produce the product. So we need to know tool constraints and incorporate just in the topology optimization by using some programming techniques. So this is know-how. Okay, so these are the steps. It is also the work from my MTech student. So here it is a problem definition, data collection. We can go all this one. Once you get FEM modeling, we can use this scripting language, TCL tool. It is called TCL stands for tool command language. You can even use Python, but Python is different. But this one is coming with graphical user interface. So it is better to use this one. Then we can go for, you modify everything in this, then we can go for topology optimization, then design incorporate, then you can go and you can validate the design. Maybe if you feel that this is the edges are weak, then you can modify this, then you can write the comment on your own and you can introduce it, and you can get the topology. After that, you can get the topology optimization, what you are getting. So it is kind of like modification, patching up here and there, but I'm not very sure, but we are trying it right now. For example, this is the gripper. It's a very, very simple mechanical gripper. If we can take this one, it is a dynamic component and it got 3, but it is dynamic moving. Everything is moving, the gears and this and that. So we take that, this one, and the gripper point, this the third part 1, 2, 3. Then we just go for, first of all, we have to go for like FEM analysis and all. So, okay, we just we use conventional software, and like that we can go and this is the final topology optimized result we got. Look at this. See, you can just redesign it, just making this short, reducing this sharp edges, the holes and all. But after that also, what you are receiving after this is also manual, right? This design is done by a designer. After that, you need also a designer to do this. But we do not know. We only know the weight is reduced, but we do not know how. See, for example, you can see here, this part, it is very fragile because see this gap and all, it is not necessary. So to correct this, we can apply our own coding to correct all these. Then we can go for again topology optimization and we can modify something. We believe this so we are doing it currently, this coding. Okay. So the same thing, like another part, see, this is the result from a topology optimization without TCL commands. And this one, it looks really very funny shape after this. So what we can do, see this, we can just make it straight or like that, or we can make a curve. That's all we can do. This is manual limitation, but we can just make a program to eliminate all these, or we can just give an instruction where the goal should be and how we can modify everything using our programming, introducing the TCL script language technique. Okay, so this is how the scripting language looks like. Looks like a little bit, yeah, it is a high level language, so you can easily understand, but I think it is visible or not. Okay, so yeah, it's not very difficult. And you can use this TCL scripts with HyperMesh. It's possible. Okay. So these are all the things we are currently doing. We are unable to produce you or show you a good result. Okay, we have done this, we got this, and it is perfect. No, we are still working on it, but excuse me, I can't produce any interesting object in front of you to discuss with. So what we can do is just after finishing this, we can just use additive manufacturing. Then we can see the difference between the manual. I think we use the software, and we can find it out the solution with only software and with generative design and with the corrected code. Which one is better? And life cycle, I have no idea. We have to do this, or we have to make another programming, what to do with that to support the direct digital manufacturing. Okay, I think that's all about my work. Thank you very much for hearing.
Thank you very much, Dr. Fathima, for your presentation. At this point, I'll open it up for questions. One of our students, Dr. Fathima, asked about FEA, and I answered that it's finite element analysis, or FEM, finite element modeling. But there's a question about the types of metal alloys that you are using for 3D printing or other types of manufacturing. And also, do you create new metal alloys as well?
Sir, no, it is completely design software. What we are working is only in the design software. We are not at all touched in manufacturing side.
Okay, good. In the design software, can you specify the type of alloy? Does it have the physical properties or?
Yes.
Okay.
Because we need to see, for example, for this, we need to give the properties of the material. Otherwise, it can't evaluate. It can't do anything with that.
Okay. So I believe her question is also about, like in the software, did you choose any specific type of metal alloys in the analysis?
Not really, because we are just testing our ideas. That's all. Okay. Materials we need to add because it's not so easy. It needs years to complete everything. But we just take one or two materials, and we want to prove our theory. Okay, we are in a right direction, and we can do this, something like that.
Okay, great. So this is just the first step.
Yes.
Sure. And we also have another question. Did you work for the width optimization of fiber reinforced composite structures also? So have you done any?
No, sir. No, not at all. We are not concentrating on metals. Suppose if you give that material properties and everything, we can use, once the software is ready, we can apply the, we can just feed in the properties, then we can see how does it work, which lattice structure or which concept we can make it. This is purely about the product. This is about the product. but that one is purely about the design.
Okay, okay.
It's a design. Suppose if you give the material, then the artificial system will, intelligence will recommend you like, okay, you can go for this for material, something like that. We need a lot of databases. We need to create.
Okay, very good, thank you. Are there any other questions? Again, feel free to type
questions, comments, anything.
Hey, this is Jeff from SSIE Binghamton. So I got a quick question about this. Yeah, this slide is good. I got a quick question about selecting the lattice structure. So could you please give more insights about, let's say, what type of lattice structures is kind of automatically selected, or users got some preferences? What is the algorithm that the software can automatically recommend the lattice structure type for you?
Okay. What we are trying is, it is not yet completed. For example, we try to create the lattice structure. For example, the unit cell, unit cell for each and every material is different, BCC, FCC, whatever you get. So if it is FCC, there is an advantage. Why the material is stronger, there is a reason, because it's a material structure. So what we are planning is, we have to go in line with this material structure, basic structure.
Okay, thank you.
Is that okay?
Yeah. How many? So another question is, how many existing lattice structure currently included?
It is not. It is not how many lattice structures. Sometimes we use the same structure. I mean, for example, you take one for first one, two, second, third, and fourth, something like that. You can choose anything. If there are like 4 types, we just have to apply and we have to find out, because we are creating a database for the AI system. Once it is ready, then it will give you a suggestion. Okay, this for aluminum alloy, for example, some aluminum alloy used in for the space application, it would be better if you use this one. That's the idea. Still, we are testing 1 or 2 what we are doing here, because it's a lot of work. It's not so easy to create a unit cell. It's very, very difficult.
Exactly.
It takes long time. Yes, long time.
Yeah, thank you very much. Yeah.
Thank you.
Thank you, Dr. Naik. We also have one suggestion from one of our colleagues for zero waste policy. When you actually print, not right now because you're still in the modeling phase, her suggestion is to potentially donate it to organizations like Makerspace, not-for-profit artist organizations, creativity and design centers, inventive initiatives, and so on, just to protect the environment and to prevent those wasted material from entering nature and creating any hazards for us. I'm not sure if those kinds of organizations exist in India, but I'm sure you have something where you can do some donations for these things. Just one comment and suggestion from one of our colleagues here.
Yeah. Thank you. I understand this. Yes.
Yes. Any other questions, comments, feedback, suggestions? Again, please feel free to unmute yourself and ask, or type it in the chat.
Professor Mohammed, I have a question for
yes, please.
Professor Fathima. Professor Fathima, during the analysis stage, when you use finite element analysis in specific, have you integrated, or do you consider integrating thermal analysis along with structural analysis? Because I think thermal analysis or thermal integrity of the components may be critical for space applications. What is your thought on that?
Yes, sir. Certainly, yes. I agree with you. But right now, because it is a very big topic, as you know, that design is not an easy topic. There are like different aspects, thermal, corrosion, so many aspects are there. we need to pick up, yeah, if it is thermal, yes, for space applications, it's certainly thermal analysis are very, very important. I do agree this one, but it is all like step by step, just we are exploring the possibilities and we are trying to implement some concepts. That's all we are doing right now. Thank you for the comment and the suggestion. Thank you.
Thank you, Professor Fathima.
Thank you.
We have another question in the chat. So you are considering types of materials to print with the right lattice according to the material's atom structure? Is that how?
Yeah, as I told you earlier, I have not printed anything so far because of the pandemic situation, and I have not printed anything, but I plan to print some samples to support my theory. If I have done that, and I will let you know. So far, I have not printed anything. Just I have the design, some ideas, and I want to just check that one, the possibilities and all. That's all I'm doing right now. But definitely we need to do, because if we claim that our theory is good, so we need to prove that theory is correct, right? For this, we need to go for that. Thank you.
Okay, very good. Thank you. Okay, so thank you very much, Dr. Fathima, again, on behalf of Binghamton University and VIT. Dean Vasudevan and I would like to thank you for your contribution to our webinar series, and thank you for your presentation. It has definitely inspired quite a few questions. So we look forward to hearing more about your research results once the pandemic is over and you have the opportunity to start printing things.
Yes, sir. Yes. Thank you very much for giving us an opportunity to print.
Thank you.
Represent our work. Thank you so much.
Thank you. And before we conclude, I just would like to remind everyone about next week's presentation. I'll share my screen. So we're delighted next week that we will have one of our senior doctoral students, Gurvinder Singh Kinda. He's a PhD candidate working with Dr. Mark Pollux and the Center for Advanced Microelectronics Manufacturing. And he will talk about reliability of inkjet printed silver nanoparticle patterns, coated mesoporous silica PET substrate. So it's again 1 week from today, same time, 8:30 a.m. Eastern Standard Time and 6 p.m. India Standard Time. So we look forward to Gurvinder's presentation, and we hope that many of you will be able to join us and share this with your students and colleagues. Thank you, everyone.
Thank you very much, Professor Muhammad, and thank you, Dr. Fathima, for your great seminar. Thank you.
Thank you, sir.
Have a nice day. Thank you.
Yeah, you too, sir. Bye. Thank you.